In Calculus 1, we used the Riemann sum to derive the definite integral. I wanted to find the area under a curve, so I broke it up into an arbitrary number of rectangles of varying widths. And by finding the area of each rectangle and adding them up, we got a reasonable estimation for the overall area. By taking the limit, we got the exact area. Now, one of the key terms in the process was this guy right here, the norm of the partition. Now, the norm of the partition is the magnitude of all of these widths, the norm being the largest such magnitude. So if the first width is delta x1, the second delta x2, and so on, then the ith width would be delta xi. And so we do a summation from I equal 1 to n of each of these areas. By taking the limit, that means they're all approaching 0 in size, and I know I get the value of the definite integral. Now suppose that we took the ith rectangle and then we divided it up randomly, let's say into m partitions. So if I said, well, if I take the sum from j equal 1 to m of all of these guys, well, what should we call them? Well, let's take this guy right here, and let's say that width is delta yj. So if I said delta y1 plus delta y2 plus delta y3 all the way up to the top, that should give us exactly the height of this, which would be the f of xi. Now, it's kind of a strange notation, but the idea being, I did this using just rectangles going across. What if I also made them rectangles going up and down? Then we would get potentially two sets of sums here. So if I said this width is delta xi and this width is delta yj, then the area of this piece, let's call that area delta aij, area ij, which is clearly the product of delta xi and delta yj. So what I'd like to do is restate the Riemann sum using two sets of summations. So with this said, I can adjust this slightly and say the summation itself now would be the sum from I equal 1 to n of the sum of j equal 1 to m of delta xi, delta yj. Okay? So what I'm basically doing is saying, from the first rectangle, add up all the delta y's, and that gives me my first rectangle. Then start again, add up all the y's, and that gives me my second rectangle, and so on until I've finished all of them. If I look at it this way, then what would the limit in this case be? In this case, the norm of the partition for this problem here would be the largest such area. Before it was the largest width, now it's the largest area because we've changed the setting. So if I said, well, what is this? Well, let's see. If I rewrite this as follows, 1 to n of, 1 to m of, and I put the y's here, then by adding up the first one, I get f of x1. Then by adding up the second one, I get f of x2 and so on. And then putting this on the outside, if I consider this, this will give us the integral of the integral, but with an integrand of 1. The outer integral of, for the x's are still going from a to b, but the question is, what are the y's doing? They're going from 0 to f of x. And I'm integrating dy dx. Now, think of this as being bracketed off. If I perform that inner integration, what I will get is the integral from 0 to a of y, ranging from 0 to f of x dx, which when I evaluate it will give me the integral from a to b of f of x minus 0 dx. And now we're back to the starting point. So this is part A. I will do a second part shortly.